This presentation is mainly about dynamic subgraph isomorphism and how Oberoi and his team have countered this problem. Mainly subgraph isomorphism was used in static graphs traditionally, but to study dynamic graphs, Oberoi and his team used a snapshot-based representation where a chronological order of snapshot was used to detect induced subgraph isomorphism, and this was mainly done for applications requiring a temporal sequence of graph evolution. Now, we need to understand how their approach was different from the previous works. Firstly, it used a node mapping, which means that they were prioritizing node mapping over the traditional used edge analysis, leveraging the static nature of individual snapshots while considering their chronological order. Secondly, they were using an efficient pruning strategy. What that means is they use the knowledge of previously matched nodes to reduce the search space and improve efficiency. And thirdly, while they were using the VF3 code, the existing VF3 code was further well established and well modified to accommodate for the dynamic graph constraints. And how is this better than all the previous ones? Firstly, performance. This used to outperform the existing methods, especially when dealing with larger graphs or datasets. Secondly, a chronological order was maintained in dynamic graphs where snapshots were used to see the progress of the dynamic graph over a large period of time. Thirdly, is the scalability. This not only is good for Oberon's technique was not only good for small scale, but also for large scale applications having complex graphs.
Next, let's discuss the input and output of the code provided by Oberoi and his team. The algorithm basically maps the edges and the nodes from the pattern graph H to the target graph G. So this basically provides us with the isomorphic subgraphs between the two. Firstly, let's understand the format of the input requirements. The code basically expects two files. The first file will be for the pattern graph, which is H, and the second will be for the target graph, which is G. For each file, we'll have the first line, which will be the number of nodes, n. The number of nodes of the graph and the subsequent n lines will basically tell us the details of each node. The details include the node ID followed by the attributes of the node. Each node has two main attributes, the number of outgoing edges from that node and the details of each edge. Now let's understand the output of the code. Firstly, the code basically provides the subgraph matches between H and G. If you look at the first line of the output, you'll notice that timestamp 0 basically maps the node H to G. So for the node H, for the node in H, we have V1, which is mapped to the corresponding one in the target graph, which is V100. Similarly, after the node is mapped, the edges are also mapped. So R4 is mapped to R34. In this way, the subgraph matches are found.
Assalamu alaikum. The study by Bourgeois utilized temporal graph models to analyze the intricate gameplay between two teams, Spain and Argentina, in a championship game, and it focused on the relationship between interaction diversity and performance. Now, it analyzed graphlets, which are small, recurring patterns of player interactions, and by comparing these, we can see the distinct strategies of the two teams. By analyzing the graphlets, we can see that Spain has a greater range and thus is more flexible and can adapt to the ever-changing situation on the court. By observing and seeing the transition profiles, which basically show us how the graphlets evolve over time, we can see that Spain demonstrates a wider range of transitions and which allows them to adapt better to the changing situations on the court. The power of this is basically what gave Spain the competitive edge over Argentina. It was their enhanced player interactions, which gave them strategic adaptability, which leads to enhanced performance.